Now, what's the procedure of solving the Schrödinger equation? Now, say if I have been given a problem, we will be doing after this, after knowing the steps, we will be taking a few examples. We'll talk about some actual problems of quantum mechanics. But what are the steps of solving the Schrödinger equation? You already know, but let me just summarize it. So what is the step number one? Step number one is that if you have been given a problem and the problem is usually in terms of the potential. So what will happen? You will be given some kind of a potential as a function of x. And you will be told that, okay, there is some particle like electron which is moving inside this potential. And the first step is going to be corresponding to that potential, you solve this time independent Schrödinger equation because you want to get that time independent part. The time dependent part you already know. And the psi can be multiple psi. It can be several eigenfunctions corresponding to several energy eigenvalues. Energy eigenvalues can be discrete or continuous. Then what you do, you find capital psi 1, capital psi 2, capital psi 3 and so on. What do you do to find that? You multiply with the time dependent part. So you already got psi, you multiply that with the corresponding time dependent part, which is e to the power minus iota et over h bar. Okay, then you get the capital psi. Okay, now once you get the capital psi, there can be several such capital psi because there can be several such small psi, psi 1, psi 2, psi 3 and so on. So corresponding to that you can have several capital psi's, and what you do to get the general solution, you simply take the algebraic sum of those. So coefficient Cn times the capital psi and you take the summation. And if it is not, say, discrete, if it is continuous, you take the integration. Okay, so with that, let's try to do some problems. Easiest one, let's talk about a free particle. Now, in case of a free particle, what do I mean by free particle? Free particle means this particle is not under the influence of any force. Force is basically zero. If my force is zero, what will happen to the potential energy? What will happen to the potential energy? So force, as you know, is this negative gradient of potential energy, assuming we are talking about conservative forces. If this is zero, it means V has to be a constant. It can be any constant. I mean, see, V is never absolute in itself. You can talk about the change in potential energy, but if you have to talk about, say, the energy, the potential energy value, then you always have a reference. You can't have a potential energy without any reference. Okay, so it's basically the potential energy. If I say the potential energy is constant, I can assume the reference to be anything. I mean, I can simply assume it to be, say, 1. Doesn't matter. I can assume it to be 0 for simplicity. So just to simplify things, I'm assuming my V equal to 0. V has to be a constant. Let me assume V equal to 0. Okay, so for a free particle, potential energy is 0. So what's the first step I have? What's the first step? First step is time independent Schrödinger equation. So time independent Schrödinger equation will be minus h bar square by 2m. Basically this h cap psi equal to E psi, and h cap is, kinetic energy plus potential energy. This is 0. So what you have is only the kinetic energy part, which is minus h bar square by 2m into del 2 d2 psi by dx square equal to E psi. So calculate the energy eigenfunctions. So small psi's are energy eigenfunctions basically. Can you solve this equation? It's a double derivative equation. How do I solve it? So just let me do some manipulation. take 2m here, h bar square here, so this becomes minus 2me over h bar square. And let me call this quantity as some k square. I mean, it's some constant. So that will make, let me take this on the left hand side, this thing, that will come plus. So this is what I have to solve. Okay, how do I solve it? It's the simplest second order differential equation. How do you solve this equation? Now, I mean, let me assume that the operator d denotes del by del x. So this will be basically d square acting on psi plus k square times psi equal to 0, right? If I assume that d denotes del by del x, so d square will be del 2 by del x square, correct? So let me take this psi here. So d square plus k square psi equal to 0. If I want non-zero solutions of psi, non-trivial solutions as we say. Non-trivial means which are not completely 0. So if this is not 0, then this has to be 0. So basically you get d square plus k square equal to 0. Okay. How can you write this equation? There's another form I can write this equation. So d is this del by del x, right? So what if I write this? Does it denote the d square plus k square? This thing? You know, iota square is equals to minus 1. So d2 multiply this, you know, a plus b, a minus b, so a square plus b, a square minus b square. But iota square is minus 1, so that makes it plus, so you get the same thing, right? So independently, this into this must be equal to 0 basically. This into this, because this is not 0, so either this has to be 0 or this has to be 0, because this is non-zero, I know that. I'm talking about solutions which are non-trivial. So what do I get? What do I get? So d by dx plus iota k psi equal to 0. What will be my psi from this equation? This is a first order differential equation. Basically you have converted a second order into first order, and this is not a very difficult equation to solve. How do I solve it? Can you quickly solve this equation? It's easy. So d psi by dx plus iota k psi equal to 0, right? D psi by dx is equals to minus iota k psi. So take this here, d psi by psi equal to minus iota k dx. Integrate, what do you get? Some exponential. Okay, some exponential of e to the power minus iota k into x, something like that. Yeah, there will be some integration constant also. So from this, let me just write down the solutions that we will get. So corresponding to this plus, when I solve this one, so I get something like this. Let me write it as psi plus a into e to the power iota kx, and corresponding to this I get psi minus, which is this. Okay, so you will get two types of particular solutions. One corresponds to this, other corresponds to this. So what will be the general solution? You have two particular solutions. The general solution of this equation, not the actual Schrödinger equation. So that will be this. Yeah, algebraic sum of the two. So this denotes a wave moving in the positive direction of x-axis, e to the power iota kx. You know that e to the power iota kx, it's a function of a wave. whose wave number is k. So e to the power plus iota kx denotes a wave which goes in the positive direction of x-axis. So it's a traveling wave. And e to the power minus iota kx denotes a wave which goes in the negative direction of x-axis. Again a traveling wave. Okay. Now what about this k? So k is related to the energy, right? So what we can write, e to the power minus iota et over h bar can also be written as e to the power minus iota h bar k square by 2m, right? Because e is h square k square by 2m, so h will cancel. So you will be left with 1h. Get this. So what I am doing now, I am going to multiply. So we have already got the time independent part. I am now going to multiply the time dependent part. E to the power minus iota et over h bar. And E is related to k. We put it there. What do I get? I get this. The total wave function, which is a multiplication of independent and time dependent part, that will look like this. Yes? Kx minus, and there was a minus, so I took the minus out, so this becomes plus. Okay? So k equal to under root of 2 me over h bar, assuming k is a positive number. So as I said, one of them is the wave going in the positive direction. This represents a wave in the negative direction. So traveling wave has variation with x as well as with time. Yes, that's how the wave equation looks like, right? So it will be different for different x, and for the same x you will have oscillations with respect to time. That's why both the parts are here, x and time. But this, I mean, yes, I can keep working with this, but let me try to make it more compact. Just for the simplicity, now I have one positive wave, one negative wave. Let me write, and k is a positive number here, so let me write it in a compact form like this, and let me vary the k from minus to plus. Okay, so in this equation I assume that k is a positive number, and I explicitly wrote the negative part and the positive part and just sum those up. But I could have simply obtained the solution as this thing. So simply a into e to the power iota kx minus h bar k square by 2m into t, which is basically this thing, but I have allowed this k to vary from negative to positive. If I make this k say negative, so minus minus, so you can take the minus out, so that behaves like this. If k is positive, so that behaves like this, right? So you have compacted both of the scenarios in the same thing, minus as well as plus. Okay, even if you do keep on using this, you will reach the same solution, right? But this is more compact, easier to understand, so I'm just writing this. Okay, so let me write this thing as omega. So this you may know, right? E to the power iota kx minus omega t. What does omega denote? Some kind of angular frequency. Yes, you might have seen these equations. Y is equals to a into sine into kx minus omega t, something. So this is a traveling wave equation, but we can't have sine or cos. The reason you already know, right? But we can have e to the power iota. In fact, here we can also have sine and cos, but e to the power iota is just easier to work with. That's why I'm using it. Okay, what's the omega? Omega is this thing. So basically, what will be the omega? Omega will be E by h bar, or you can say E is equals to h bar omega. And k can be plus and minus, right? So I assume k square equal to some 2 me by h bar, but because k can now take positive as well as negative, so it will be plus minus under root of 2me over h bar. Now this is the solution of the free particle. Yes. Now let's try to see whether this solution makes sense or not. I'm gonna evaluate velocity. Let me evaluate the velocity. So this is a wave equation, right? A e to the power iota kx minus omega t. And waves have velocity. What's the velocity of a wave? How do you calculate? So wave is like this. You know, it's moving. So if say this is the pattern at t equal to 0, at t equal to say some t1, the pattern will be something like this. Assuming this is moving in the positive direction. So we'll shift. Something like this. Okay. So wave has shifted. And this has some velocity. So the pattern moves with some velocity. That's called phase velocity. And the phase velocity is given by omega by k. Velocity of a wave, it's simply given by omega by k. I can derive it, but I would like you to, search about it, why the velocity is v is equals to omega by k. So it's called phase velocity. It's with which the traveling wave moves, omega by k. So let's try to evaluate this quantity omega by k. So omega by k, and of course the magnitude, let me just only focus on the magnitude of the velocity. So omega by k mod, what is omega? Omega is this thing, this h bar k square by 2m, and you have k here. So k and k will cancel, so that will be h bar k by 2m, and k and e are related, so you can put this k in terms of e from here, you get under root of e by 2m. That's what you get. So what we are saying that the free particle is being represented by a wave which is moving with this velocity. Okay? Free particle is behaving as a wave which is moving with this velocity. I still don't know if this picture is correct or not. Okay? I'm just trying to evaluate whether this quantum mechanical solution makes sense or not. Now, let me assume that there is a classical particle which is moving with some velocity v. What will be the velocity? Say if I know the energy of the particle, it's a free particle, so it will only have kinetic energy, potential energy is 0. What will be the velocity of the particle in terms of energy? V of the classical particle. How do I calculate it? So I know that E is equals to half mv square. It's just the kinetic energy. So what do you get? V is equals to 2e by m under root. Whoops, these two don't match. Yeah, we don't match. What's the relationship between this phase velocity and the classical particle velocity? So the relation is this. So phase velocity, as calculated from quantum mechanics, it is only half of the classical velocity. Okay. But I do know that this classical velocity, although it's classical, but it does work in some cases. I know that for a fact. Okay, E equal to half mv square, it does work. But quantum mechanics is giving me something different. It's giving me just half of that. So there's some loophole. Something is wrong. One more thing, which is bigger than this, is this thing. Look at this wave function. Remember, we talked about a well-behaved wave function in the beginning. So how should a well-behaved wave function look like? Well-behaved wave function should be square integrable. Yes, should be square integrable. So is it going to be square integrable? Square integrable means basically this thing, 1 or any finite number. If it is not 1, that's fine, but it should be at least finite. Square integrable means the square integration gives you something finite. Let's look at this thing. Can you tell me this thing is going to give me something finite or not? What do you have? Mod a square into basically 1. Take the mod of this and do the square. So basically you are doing a e to the power iota something into a star into e to the power minus iota something. This and this will cancel. This will become mod a square dx. Minus infinity to infinity. What will be the answer? Is it a finite number or infinite number? Mod a square, and a is a non-zero number, because I'm not talking, if a is 0, then psi becomes 0. So a can't be 0. I'm not talking about trivial solutions. So a is a finite number, mod a square is a finite number, and you integrate that number from minus infinity to infinity. Basically, you are summing up that number from minus infinity to infinity. Keep doing that. So what do you get? Infinity. Okay. So this is infinite. Not a valid solution. This does not correctly represent a particle. So many times you find classical particle, this free particle, they represent it as a plane wave. Yes, plane wave has significance in the solution of the free particle, but we are not yet there. This is not the full story. This is violating the square integration condition. So this can't be the realistic wave function of a free particle. So then what is a realistic wave function? By the way, the energy here, the energy is an eigenvalue, right? Is it discrete or continuous? This E. Did I put any condition that makes E discrete? No. Free particle does not have any boundary condition. So whenever you have a differential equation, you also need to put some boundary condition. At minus, say, x, some minus x and some plus x. But we did not do that because it's a free particle. It's free to move from minus infinity to infinity. Potential is 0 everywhere. We did not have to put any restriction on this free particle. Can move anywhere. So no boundary condition. No boundary condition. So E is simply some number. Can be any number. So E can be any real number. Negative, positive, 0. It won't be a complex number, but it's a real number, but not a discrete number. So if I now have to find out the most general solution of the differential equation of this Schrödinger equation, what will that be? I told you, what was the step 1? Step 1 was you find out the eigenfunctions of the Hamiltonian. Step 2, you talk about this time part. Step 3, you simply multiply the time part with the time independent part, you get this. But the story does not end here. This is not the most general solution. The most general solution will be integration, right? Integration of this psi with respect to x with some multiplication of the coefficient. So let's see. This is going to be the general solution. So what you have done basically, this thing is coming from the capital psi. Okay. There was a constant a. For simplicity, let me assume that it is equal to 1. doesn't matter. If I have a wave function, you multiply this with any constant number, doesn't matter. You multiply with a, b, whatever, doesn't matter. It does not change the state. So that I have assumed that to be equal to 1. And what is this phi k? So you remember that what I wrote, CL psi of x e to the power minus iota et over h bar dl. This is what we wrote, right? And this was my capital psi. So this is capital psi, and corresponding to this c, I have, say, this phi, and this dl is dk. Why I have written k here? Because look at this thing. So psi, it's a function of x, but it is also a function of this k. Okay, so I'm going to integrate over this k. So k becomes kind of my index, right? What do you integrate over? So basically you have different energy eigenvalues. But what is changing the energy eigenvalue? So E is equals to h square k square by 2m. If I use different values of the k, k1, k2, k3, k4, I get different values of the energy. And corresponding to those energies, I had to sum this up. Or indirectly you can say corresponding to different values of k, I am summing this up. Okay, so that's why the integration is over k. Okay, k is a continuous because energy is continuous, and E equal to h square k square by 2m. Both of them are continuous. So you simply, this is the coefficient, or the weight factor you can say. This is the function, you sum them up. What about this under root of 1 upon 2 under root of 2 pi? This is some factor I have put here just for some mathematical simplicity. You may be able to appreciate it later on, but just for some symmetry I have kept it here. You can completely remove it, up to you. But I can multiply, in fact, any constant here, doesn't matter, because you know I can multiply any constant with the wave function, it does not change anything. Okay, so this is the form of the free particle most general solution. This is actually a wave packet. We know that the free particle, it is not a plane wave, it is not a delta function, it's a wave packet. This is the equation of the wave packet, a mathematical representation of that. Now how does it represent a wave packet? We will see that. Okay, so we already talked about it, so we can calculate this phi k. Now how do I calculate this phi k? See, if I know this phi k, I will be able to evaluate this function, correct? But I need to know these coefficients. People who are already familiar with the Fourier transform, you probably know what I'm trying to say. This is actually inverse Fourier transform, okay? But let's not go into that terminology. So I need to calculate this phi k. How do I do that? So now we know that the psi x comma 0, let me put t equal to 0 here. So this part is gone, right? I have more simplified relationship here. Simply some weight factor into e to the power iota kx summed up over k. Very simple. Yes? How do I calculate the phi k from here? Phi k can be calculated by this thing. You can take the inverse Fourier transform. If you do not understand it, don't worry. We are going to do some example, and I won't use inverse Fourier transform terminology there, but you will be able to see how this form can be reached. But we'll do that in an example. For now, you can simply think of it as some kind of a formula. Okay, so this is basically inverse Fourier transform, and this factor, if I keep 1 upon root 2 pi here, so in the inverse Fourier transform I will get 1 upon root 2 pi. So that's why I kept it for the symmetry. But you can calculate phi k from this formula. This is called inverse Fourier transform. Okay, Okay, when I go from here to here, okay, so this is one way to represent the wave function in terms of psi. And I represent psi as a function of x and time. Or if I'm talking about psi x comma 0, so I represent it as a function of x. But wave function information can be contained in these coefficients. Okay, so you have phi k into e to the power iota kx. Remember the reciprocal lattice. So we said that any periodic function can be written as summation of some coefficient times e to the power iota gx. Right? It is the same thing but the integral form of that. E to the power iota kx times the coefficient. So all the information of this psi lies in these two things. Okay? So if I want to represent the same information, I can also represent it as phi k. So phi k is equals to this. When I represent the wave function in this form, this is basically the coefficient, nothing else. But all the information of this wave function is still preserved here. So whether I use this thing or this thing, I do not lose any information, as was the case in the reciprocal lattice. Okay? So it's the same information. So this is called the momentum space representation of the wave function. So you are representing the same wave function, but you're not representing as a function of x, you are representing it as a function of k. Basically, you're talking about those coefficients. Why momentum space? Because k is basically momentum. You know, p is equals to h bar k. Momentum space representation or k space representation both mean the same thing. Information is not lost. It's another way of representing the same wave function. Okay? So let me now, because I know that this is a wave packet. Okay, why is a wave packet? Can you see this thing? So it's basically, you have some summation, right? And then you have some constant, say c, and then you have some e to the power iota kx. So you are taking the algebraic sum of plane waves of different wavelengths. So every k will have a p associated with it, and every p will have a lambda associated with it. You know that p is equals to h by lambda using the de Broglie relationship. So I have several plane waves here of different wavelengths or different k values, and I'm simply taking the algebraic sum of that. What does that make? That is basically the wave packet. That's what we talked about, right? We talked about that a wave packet will have several wavelengths in it. Do you see those wavelengths? Yes. This is. Okay? Now this wave packet, it's a more correct representation of the free particle, and it's going to move with some velocity. Let's try to evaluate its velocity. But before we go into the velocity calculation, let me talk about one more thing, which is called dispersion relation. So dispersion relation is the relationship between E and K. So in this case, in a free particle case, you know that E is equals to h bar square k square by 2m. So that's the dispersion relation. Why the name dispersion will become clear in a moment. But relation between E and K, or you can say omega and K also, because omega is also related to E. That's called dispersion relation. So let me show you how this looks like. So if I plot E as a function of, say, K, so how will it look like? So E is proportional to K square. It's a parabola, correct? Something like this. E as a function of K, or you can say momentum also, because K is proportional to P. So this is for a free particle dispersion relation. But in general, see this wave packet concept, it's not only valid for a free particle, it's valid for, so if I have an electron moving inside say a crystal, electron will also have a wave packet, and the wave packet will look exactly the same. The only thing that will change is the relationship between E and K. So for a free particle, parabolic relationship, but if I have an electron which is moving inside a crystal, this dispersion relation, it may change. So it may be some nonlinear function like this, may not exactly be a parabola. So E versus K relationship might be a little different. So whatever is the case, we can still use this equation in the same form, whether it's for free particle, whether it's for an electron moving inside a crystal. Because this equation is simply saying that you are summing up different wave functions, so it's the same thing. Okay, so now let's calculate the velocity of the wave packet. Let's talk about this coefficient phi k. Now I'm going to assume, and there is a reason behind that, this phi k is non-zero only in a small region around a point k naught. Phi is a function of k, yes? And I'm assuming that there is some k naught and phi k is only centered around that k naught. It means if I go away from k naught, say if I go in the positive direction or in the negative direction, phi k will have a small value, but around k naught it will have a large value. The reason is that, so I'm saying something like this. So phi k looks something like this. Why? This k denotes what? Momentum. Yes? K denotes a momentum, or you can say the velocity, the phase velocity of one particular wave. It depends on k. How? V is equals to omega by k. Yes? Omega, you know that h bar k square divided by 2m divided by k, you get the velocity. So velocity is totally a function of k. And it should be, right? I mean, k denotes the momentum, so velocity will also depend upon the k, the momentum. So if I have very large range of k, what does that mean? I have very different velocities. So what I'm doing in a wave packet, I have several waves with different velocities or momentum, and I'm simply taking algebraic sum of those. What will happen if the velocity of all of these waves are too different from each other? What will happen? I have many traveling waves which are traveling with very different velocities. What will happen? Disperse. They are going to disperse. So you won't see a wave packet then. So wave packet will remain a wave packet when most of the components will have similar velocities. If components have two different velocities, so this is moving like this is left behind, so your whole wave packet is just going to fall apart. You get my point? Okay? In reality, yes, the components will still have different velocities, but phi k will still look something like this. I'm not saying it's too much centered around k, but it has a peak around some k naught. This is 0 here, this is 0 here. So the coefficients of those different waves, what does this denote? The coefficient. So basically this is a weight factor of a one particular wave. So what do I do? Plane wave times weight factor. Plane wave times weight factor. What is that weight factor? Phi k. And I have assumed that the weight factors only around a small range of k are non-zero. So all of these components have kind of similar velocities, and these weight factors are negligible or very small values, so they don't come into picture. Okay, so this is going to maintain the integrity of that wave packet. Yes, it will still disperse, but will not completely fall apart. Okay, so if I can assume that, then I can assume one more thing. Because my phi k, it's centered around this k naught. So what will happen to this integration? Yeah, there is some time factor also, say minus omega t here. What will happen to this integration? I can safely say that this integration, I only need to evaluate only in this range, because this phi k is 0 here, 0 here, so these limits of integration, this is k actually, so from minus infinity k to plus infinity k will get restricted to this range. Yes, so I'm only talking about this particular range, a small range of k values centered around k naught. Now if I restrict myself only to a small range of k values, the dispersion relation, which is the relation between omega and k, that can be simplified. How do I simplify that? Say I have omega some function of k. We know that in a free particle it's parabola, or in an electron case moving in a crystal it can be some nonlinear relationship. Yes, so say I have this nonlinear relationship. I'm taking a most general case, say this is my k naught. Okay, now if I restrict myself to only a small region of k values around this k naught, so I am somewhere here. Yes, if I am somewhere here, how does this portion look like? Does it look like almost linear to you? Yes, yes. So this is what I'm going to do. Although the full relationship between omega and k, it is non-linear, but if I pick a small portion of that, that is approximately linear. Okay, so I'm going to linearize this thing. How do I linearize? This is basically a straight line. How do you find the equation of a straight line? You need to know the slope, and you need to know at least one point on the straight line. What is that point? Corresponding to this k naught, I have some omega naught. Yes? Okay, so I have one point. Now how do I find out the slope? By the way, I do have this function, omega is f of k. I do know this relationship mathematically. So what is the slope? What is the slope of this straight line? If I draw a tangent here, the slope of that tangent is basically the slope of this thing. You get my point? If I draw a tangent here, line which is touching this thing, the slope of this is the slope of that tangent. What is the slope of tangent? d omega by dk. This is the slope. Yes. So, but where do I calculate d omega by dk? Somewhere here. At what point? K equal to k naught. Okay. So now let me form the straight line equation. So straight line equation is y minus y naught is equals to slope m into x minus x naught. That's how the straight line equation looks like. So in this case, what do I have? Omega minus omega naught, m is d omega by dk, but calculated at k equal to k naught. What is x? X is my k minus k naught. Okay, so I simplify my non-linear relationship between omega and k into a linear relationship. And that we are only being able to do because we assumed this thing. So we get this. Yes, I took that minus omega naught to this on the right hand side, plus omega naught. This is d omega by dk, and it has the dimensions of velocity, right? Omega by k was the phase velocity, d omega by dk will still have the velocity dimension. So let me call this as some Vg. Okay, Yg will become clear later. So Vg into k minus k naught plus omega naught. Okay, now I have everything to plug back. So psi x comma t is 1 by root, this is total root 2 pi, phi k into e to the power iota kx minus omega t. Omega is given by this thing. So I plug that omega here, Vg into k minus k naught plus omega naught into t. Yes? And of course it will be approximate. So what you do, take all the terms which are not functions of k out of the integration. So I get this whole thing out which has some time dependency, e to the power iota minus this thing. And what I am left with is this thing, phi k into e to the power iota k into x minus vgt dk. Okay, now you tell me, what is this? So psi x comma t was this. Yes. What will be psi x comma 0? This. What is this thing? So psi x comma 0, it's a function, wave function at t equal to 0. So say I have, say if I take the real part of that, it looks something like this. I'm drawing psi as a function of x now. Okay, it's a wave packet, right? And say at t equal to 0, this is how it looks like. It's some kind of a function of x. Yes. What is this thing? So here you have replaced that x with x minus vgt. It's the same thing, but x is replaced with x minus vgt. So it's like if you have a function of f of x and you replace f with f of x minus x naught, what happens? If I have this function, f of x, and I want to draw f of x minus x naught, how will it look like? You simply displace the origin at x equal to x naught, draw the same function again. It's the identical function, but it is shifted by x naught. What about this? When you go from here to here, so it's a function of x, but I can write this as psi x minus vgt, comma 0. Yes? I can write it like this. So this is nothing but this. So you have replaced x with some x naught. So x naught is vg into t. So basically you are going to displace this thing with what? Vg times t. So basically this. What is this distance? Now, if I am displacing something with Vg times t, what will Vg denote? Its displacement is Vg times t. So Vg is the velocity, right, with which this wave packet is going to move. You get that? Okay, so at t equal to 0, it looked something like this, and I'm seeing that at later time t, this thing is shifted by Vg times t. Okay, so what will be the Vg? Vg will be the velocity with which this wave packet is the moving. That's why the shift is Vg times t, displacement basically, velocity times the time. So this Vg is called group velocity. That's why the symbol g. Now why this group velocity? Okay, so now you will say, I'll come back to that, but this factor times, okay, let me just write it, yeah. So you have this factor times this. So now you may have a question, what about this factor? I mean, yes, this is displaced with Vg times t. What about this factor? Does it play a role? Does not play a role. You can see that this factor is e to the power iota something. So it is e to the power iota theta basically. So this is simply going to change the phase of the complex number, nothing else. Okay, in fact, if I take the mod psi square, this factor will disappear. So the probability is still being shifted with the velocity Vg. So I don't care about this thing. Okay, so I only focus on this part, and this part is being shifted with the velocity Vg. Vg is called group velocity. Why the name group velocity? Can you tell me the reason? Because you don't have one wave, you have a group of waves which are kind of moving together. They are just holding on to each other, right? They still have different velocity, but you still see some kind of a shape and it's moving together. So it's like you have this thing, not k naught. So this is x. I'm in the x space, position space. So this will be some x naught, and the center of this wave packet is moving with some velocity. This whole envelope of that wave packet, inside this you may have several oscillations if I plot the real part, and this whole thing is moving with the velocity Vg. So this is called group velocity because it's made up of several waves. And what's the value of the group velocity? Vg is equals to d omega by dk, not omega by k. Okay, so d omega by dk calculated at k naught. K naught is that center point, momentum center point, right? Now omega can be written as e by h bar, so you can also write it as 1 by h bar into d by dk. In fact, we will be using this quite often. So say if you have a relationship between E and K, so you can simply take the slope of that, you get the group velocity. Okay. Now let me show you some animations. Will give you more clear idea. So in our approximation, we kind of assume that the wave packet moves with a constant velocity Vg because we linearize the relationship between omega and the k, or E and the k. That gave us a constant velocity Vg, and in our approximation we will have a picture like this. So my wave packet, it's moving but it's not falling apart, right? It's not dispersing, but in reality that's not how it works. You still have some dispersion. That's why the name dispersion relation. That's the relationship that's going to disperse everything. So that's how it will look like. So as it moves, it is spreading out. Okay, this is the more realistic picture. And if you talk about, say, the mod psi square, that keeps spreading. But by the way, it keeps spreading, but the area under this, it still remains the same. It is equal to 1. So area remains the same. So basically, if you want to reduce, if you want to spread it, because the area is the same, you will have to reduce the height. That's why as it moves, its height keeps reducing, because area has to remain the same. You stretch it from here, it will have to come down from the top, so that the overall integration remains the same. Integration is the area. Okay. Now let's quickly calculate the group velocity of the free particle. We saw that the phase velocity does not match the classical velocity. It was v classical divided by 2. Now let's see if the group velocity matches the classical velocity. So for a free particle, we know that E is equals to h bar square k square by 2m, and you know the relationship between E and K. So Vg you can calculate 1 by h bar d E by dk at k equal to k naught. So what do you get? Differentiate it, 2 and 2 will cancel, so that will be h bar k naught by m. H bar k naught is p, right? Or because k, you already know the relationship, you can directly write k in terms of E here. So if you plug in, do all the calculations, you get under root of 2e by m. You can check that, and this is exactly v classical. It means the wave packet picture is more appropriate. So as you have a classical particle moving with some velocity, in the classical mechanics, you have correspondingly wave packet with moving with some group velocity, but of course it is going to spread. It's not a particle located at one point. Okay. Now let me tell you a general analogous, you can say, quantities in classical and quantum. So many of the relationships that work in classical can still be used in quantum. Why? Because of this wave packet picture. So you have a classical particle, correspondingly you have a wave packet. As a classical particle moves, the center of the wave packet moves. Okay, so because of this correspondence, you can have some analogous relationships. And in classical mechanics, we talk about the absolute quantities, momentum, position. In quantum mechanics, we will talk about their mean values. Okay, so in classical mechanics, the particle has a definite position, follows the Newton's law. You know that dp by dt is equals to force. It's given by this minus dv by dx, you know, this thing. Correspondingly, in quantum mechanics, you can apply the similar relationship, but you will have to replace every quantity with its mean value. Okay, so they also follow a similar Newton-like law, but you will not talk about the absolute quantities, you will talk about their mean values. And this is possible only because of the wave packet picture. Now in some cases the wave packet picture may not be appropriate, you can't apply that, you can't apply this thing there. Okay, so you need to be careful. But yes, if I'm talking about an electron moving in a crystal, it will work, approximately work. So d expectation value of t, dp by dt is m into d2 x by dt square, but expectation value is equals to force. Force is not, of course, you won't write expectation value of the force because it's simply the gradient of the potential energy. Potential energy you already know, right? So this formula works in the quantum mechanics. So it's this picture simply shows you some correspondence. So as you have a classical particle, say at x equal to x1, you have a wave packet and its center is at x equal to x1. As this particle moves, wave packet moves, comes to x3, wave packet moves, but as the wave packet moves, it also spreads, disperses. Okay. So free particle is complete. Now I'm going to talk about another case, which is particle in an infinite potential well. A simple quantum mechanical problem, but very important to understand the band structure. We are slowly reaching our goal, which is to understand how the bands form and how the band structures work. Okay, we have already seen a lot of the theory that we will be using, but this problem, particle in an infinite potential well, this will give you some more a better idea. Okay, so when I say particle in infinite potential well, I'm talking about this thing. So I have a particle which is confined between x equal to 0 and x equal to a, and outside of that, so potential here is 0, but outside of that potential is infinity. So it's like huge walls you have here. Particles see that there are huge potential energies. Because there is a huge potential energy, it can't go into these regions, and it will be confined between x equal to 0 and x equal to a. Yeah, the particles can't have infinite potential energy, so it can't go here. Okay, so we have region number 1, 2, 3, and we need to solve the Schrödinger equation and find out the solution of the Schrödinger equation. We'll be talking about the wave functions and the energy eigenvalues. So how do we start? We start with the step number 1, time independent Schrödinger equation, which is calculation of energy eigenfunction. So h cap psi equal to E psi. What is h? H is minus h square by 2m into d2 psi by dx square into E psi, but I'm talking only about this region. So in this region my potential energy is 0, right? So that h cap is given by only the kinetic energy operator. Potential energy is 0, right? And in these regions I'm not even writing the Schrödinger equation, because I already know that there is particle can't escape. So particle can't escape this thing. Particle's wave function is going to be 0 in this region as well as 0 in this region, because there is a 0 probability of particle being found in these regions. So its wave function has to be 0. So wave function is 0 from minus infinity up to x equal to 0, and then from x equal to a to plus infinity. But in between it is non-zero, and in between I have this Schrödinger equation. Now how do I solve it? We have already solved it. Okay, so what was the solution? So you can write this, a 2me over h bar square. This denote that with some k square. K is given by under root of 2me by h bar. And I'm assuming k to be positive here, so I'm taking only the positive values of the k, and because I'm taking the positive values of the k, so the general solution is going to look like this: a e to the power iota kx plus b into e to the power minus iota kx. We have already done this. Yes? Okay. Now, in the free particle, I told you that I did not apply any boundary condition. So typically whenever we are solving some kind of a differential equation, we always need boundary condition. What do I mean by boundary condition? Let me give you a simple example. Say I have dy by dx is equals to some x. It's a differential equation, but a first order differential equation. What will be the solution? dy is equals to some x dx, y is equals to some x square by 2 plus some integration constant c. Now, boundary condition means if I know the value of y at any x, I will be able to calculate the value of the c. Yeah, say at x equal to, it is given that at x equal to say 2, y is equals to 5. So if I know this information, what will I do? So these two will also satisfy this. So 5 is equals to 4 by 2 plus c. So c is equals to 3. So with the help of the boundary condition, now I am able to find this integration constant. This is the boundary condition. Okay. If I have, say, now a second derivative equation, how many times I will have to integrate? Twice. In first order I will have to integrate once, second order I will have to integrate twice. So I will have 2 integration constants. So how many boundary conditions I will need? 2. Okay. So boundary conditions are something which we need to calculate the integration constants. Okay, so what are the boundary conditions? in this problem. Not three boundary conditions. So I know that wave function is 0 here and wave function is 0 here, and it's a double derivative, differential equation, and I can see that I have two unknown constants, a and b. Okay, so what kind of boundary condition I can have? I can have two boundary condition, one at x equal to 0 and another one at x equal to a. I know that wave function is 0 here as well as here. Yes, at the boundary wave function has to be 0 because there are these infinity walls. The wave function will be 0. Probability of the particle being found there will be 0. So that's the boundary condition I'm going to apply. Okay, so let me put at x equal to 0 psi equal to, what will be the psi at x equal to 0? 0, right? And what is my psi 0? Okay, let me just write the other boundary condition also. Psi 0 equal to 0 and psi a equal to 0. Okay, equation number 3 and 4. Now using these so using my equation number 3 and equation number 2, the previous equation, psi equal to that a e to the power iota kx plus b e to the power minus iota kx. If I plug this thing there, so what do I get? Psi x is a e to the power iota kx plus b e to the power minus iota kx. Put x equal to 0 here, so I get a plus b equal to 0. Yes, this is 1, this is 1, a plus b equal to 0. What about this thing, psi a? So this will be what? If I put a here, right, and make this 0, so I'm gonna get something like this. Let me first calculate it. E to the power iota ka plus b into e to the power minus iota ka, but I know that b is equals to minus a from here, so a e to the power iota ka minus of e to the power iota ka. That's what I get. Wait a minute. Oh, okay, so this is just the implication of this. Okay, I haven't written that down here. Okay, let me do one thing. Okay, so let's just make the use of this equation first, and then we will talk about what happens to this. So I have a is equals to b is equals to minus a, and if I plug that back in my equation number 2, so b becomes minus a, so I will have this equation, right? And let me just simplify it first, and then I will talk about the second boundary condition. So a I can take out, so this is e to the power iota kx minus e to the power minus iota kx. You can multiply this thing and divide by 2 iota. Why I am doing this? So if I multiply by 2 iota, divide by 2 iota, this whole thing is nothing but sine kx. Okay, can you tell me why? Can you see why this is sine kx, this whole thing? This thing will be equal to sine kx. Sorry? Yeah, it's the definition of sine. You can also do it from the complex number definition, So complex number is this cos kx plus iota sine kx, so you can get it from there as well. Okay, but by definition sine kx is this. Okay, so basically this e to the power iota kx is cos kx plus iota sine kx, right? E to the power minus iota kx is cos minus kx plus iota sine minus kx, right? Cos minus kx is cos kx. This is minus iota sine kx, right? And now this is 1, this is 2. You can subtract these things, you will get sine kx is equals to this. Okay, so psi x simplifies as let me write 2 iota a as some a dash into sine kx. So this is equation number 7. Okay. Now what I'm going to use, I'm now going to use this 4 in this 7 after doing some extra manipulation. So put this 4 in this 7. So at x equal to a, this will become a dash into sine ka, and that must be equal to 0. Yes, that's what I get from the second boundary condition. A dash is not 0, because if a becomes 0, my psi becomes 0. And particle is confined between x equal to 0 and x equal to a. A can't be 0. So if a dash can't be 0, what should be 0? Sine ka. If sine ka has to be 0, what is the condition on ka? Ka must be an integral multiple of pi. Yes? We have seen this. So k is equals to some integral multiple of pi. So what should be k? K should be some n pi by a, and k equal to 0 plus minus pi by a plus minus 2 pi by a, whatever. Okay? Okay. So, but do I need to have these minus values? Not really, because if I put sine kx, say, so it depends on case to case. It's not that in general you have to discard the negative values, but in this case you will be able to, because if I put say k, and say if I replace this say with minus k, so that is simply going to be minus of sine kx. Is it going to give me some new wave function? No. Eventually you are multiplying the wave function with a negative number, doesn't matter. Okay, so you don't have to use the negative set, or you can only use the negative set, discard the positive set, up to you. It's not going to give you a new wave function. If you use both positive and negative, basically you are doubling, you're double counting. Okay, so you don't have to. So I'm going to discard all the negative values here. What do I have then? So k is equals to n pi by a, because it's a function of n. I have written k as kn, index n, and n can vary from 1, 2, 3, 4, blah blah blah. Also this 0 is also not allowed, because if I put k equal to 0, what's my wave function? My wave function is k is sine a dash into sine ka, and k equal to 0 gives me psi equal to 0. Not allowed. Okay, negative not allowed. I mean, negative is allowed, but it does not give you any new information, so you discard that. K equal to 0, not allowed. So what do you have? So you start your n from 1, 2, 3, 4, and so on. N pi by a. And so what will be my En? E was h square k square by 2m. Because it's kn now, so I will have a corresponding En, and I know that kn is discrete, so will my energy be. Because you can put 1, 2, 3, 4, and you will get E1, E2, E3, E4, and so on. So k is n pi by, you can put it here. So n square pi square h bar square divided by 2ma square. This is the energy eigenvalue. So in this case, energy eigenvalues are discrete, contrary to the free particle case where E was continuous. Why this is discrete? What was the main reason? Where did we change? I mean, the Schrödinger equation looks the same. Potential V equal to 0 there, V equal to 0 inside the well. Where did the modification happen? The boundary conditions. Whenever you put a boundary condition and you confine the particle, you will see that its energy will become discrete. Try to confine the particle, energy becomes discrete. You try to confine the electron inside an atom, its energy becomes discrete. Okay? In an atom you have discrete energy levels, you know that. Because electron is confined inside the atom. Okay, what else we have? We can quickly just finish it up. Just give me 2 more minutes, although the time is over. But just let me take 2 more minutes. So how to find this constant a dash? We can find it usually to find these constants, right? So psi is a dash into sine kx. You can find this a dash using the square integration property. So what was the square integration? You can square integration, or you can say you are normalizing it. So whenever you are doing mod psi square dx equal to 1, so that's basically called normalization process. Put it this thing, put this psi in here. So mod a dash square sine square kx dx, and integration from minus infinity to infinity will become 0 to a, because psi is 0 outside this range. And you can calculate the a dash from here. You know the integration of sine square kx, right? You can write it in the form of cos, I think, right? You can do that. Easy integration. So a dash will be equal to root 2 by a. Okay. So what do I get? I get this thing. Psi x is equals to root 2 by a into sine of kx. K is n pi by a. So this is what my energy wave function is. Okay. So this is normalized. This is normalized wave function. If you take minus infinity to infinity mod psi square dx, so that's going to give you equal to 1. Okay. So how your wave functions look like? So they look like some sine of x, right? Earlier we had a complex number in the free particle case, but now we have a sinusoidal. Okay, so let's move and see what I talked about the energies first, right? Energies are discrete, and I told you that if you confine the particle more, you will have more discretization. What I mean is that by that is, if you confine the particle more, the difference between the successive discrete values of energies, that will increase. The separation between the energy values, so these energy values are separated, right? So if n for n equal to 1, it is pi square h bar square divided by 2 m square, right? For n equal to 2, it is 4 pi square h bar square divided by 2 m square, right? So there is some separation between them. That separation will increase if we confine the particle more. Okay, so first of all, if we just plot the energy as a function of k, so how will it look like? If I plot this as a function of this k, so E is a k square, right? E varies as k square, so it's going to be some kind of a parabola, right? We have seen that in the free particle case, this used to be continuous, and E would be a continuous function of this k. But now this is discrete, so E is going to be discrete, but will still follow some kind of a parabolic relationship. So something like this. Yeah. So for a free particle case, you have this solid line, but for a particle which is in infinite potential well, you won't have all values possible. All values of energies are not possible, right? We know that k is discrete. So what is the value of k? 0, pi by a, 2 pi by a, 3 pi by a, 4 pi by a, and so on, right? And if we allow a negative value of k also, so although they represent the same wave function, but just for the sake of drawing this, right, I've put minus values also, right? So minus pi by a, minus 2 pi by a, right? So what will happen? Because these values are discrete and no value of k is allowed in between, no value of k is allowed in between these, so only the energies corresponding to these k values are possible. Okay, for pi by a it is this, for 2 pi by a it is this. So these values of energy, this range is forbidden. So you only have discrete values. Okay, and what's the separation between them? uh, so separation between the energy values you can calculate as, so two successive values of energy will be En plus 1 minus En, right? So if you calculate it, right, you can put the formula right? And instead of n you can put n plus 1, and for this you can put n, right? Pi square h bar square 2m square, that comes out to be common, right? And that will give you, if you calculate it, so that this is 2n plus 1. Okay, so now there are a few observations that we can make here. First of all, as you increase your n, the separation, so this is the separation, that will also increase. So can you see that? As I increase my n, it means I increase my wave number. As I go to higher and higher wave numbers, you can see that the difference between the energies, it's increasing. So what is the first energy? So this is the ground state energy, right? The first possible value of energy is called ground state energy. Ground state. This is not allowed. This is the first one which is allowed. So first and then the second, the separation is this. But the second and third, the separation is larger. Third and fourth, separation is even larger. Okay, so as you go higher and higher in K, the separation between the energies increases if you confine the particle in an infinite potential well. The second thing is that, look at this A. What does this A denote? A is the extent of the well. A is the dimension of the well. What if my A is large? What if my A is large? If my A is large, the separation between the energies, that will reduce, right? So if you give the particle more and more freedom to move, then the separation between the energies will reduce. If A is equals to infinity, the separation becomes 0. Okay, it will tend to 0. It means the energies are going to become continuous because there is no separation, right? Almost 0 separation. But if you go in the other direction, if you confine the particle more and more, it means you make your A smaller and smaller, then the separation between the energies, it will become larger and larger and larger. More you confine, more is the separation. Okay, so you are moving toward the discretization. Yeah. Okay, so the quantization, the more you confine, the more is the quantization. Now let's also have a look at the wave functions, how they will look like. Let's see that. So what you have energy eigenfunctions, right? So what did we calculate? So we are still at the step number 1, right? And step number 1 is a calculation of energy eigenfunctions. So these things that we calculated, these are energy eigenfunctions. They all have a single value of energy. Okay, so you can associate one energy with each of these eigenfunctions depending upon the value of k. Okay, so energies, as you change n, right, n equal to 1 2 3 4, so energies are going to change, right? And there is a gap between the energy, so this region is forbidden, so this part is not allowed, so only a few discrete states are allowed, right? Now corresponding to n equal to 1, what will be the wave function? So n equal to 1 will give you sine of pi x by a. If you plot that, you will see that, so it looks like this, right? You can still see at x equal to 0 and at x equal to a, you have the wave function as 0. And if you plot mod psi square corresponding to that, so that's simply going to look like this. So this is a sine, and mod of sine will be sine square, so that will look something like this. Okay, and if you integrate it from 0 to a, you will get equal to 1, because outside that the wave function is 0. So probability is 0 outside it, and if you integrate the probability inside the well, so you will get 1. What about the second possible choice? So second possible choice is n equal to 2 corresponding to this energy level, and that will give you, so if you put equal to n equal to 2 here, so you will get a wave function like this. This is going to be symmetric. I think the book I took it from, it did not draw it symmetric, so it's going to be symmetric actually. Okay, so this plus lobe and minus lobe, they will be same. Okay, so that will look like this. So this particular wave function has a node. So the point at which the wave function becomes equal to 0, that's called a node. Yeah, so this is a node, This is a node, but this is also a node. You can check that. So if you put a equal, so if you put x equal to a by 2, right? Put x equal to a by 2 here, right? A by 2, and then you, what is your n? N is equals to 2 in this case, right? So 2 pi by a into a by 2. So what do you get? A cancel, right? And 2 cancel. So you'll get something equal to sine of pi, that will be equal to 0. 2 pi by a and a by 2. So a cancel, 2 cancel. So you'll get a pi, sine of pi. Sine of pi will be equal to 0. So you have a node here. Yeah. Similarly, if you see the mod psi square, so this negative will become the positive, right? Right. So this will invert. So you have this. Similarly, when you go higher, n equal to 3, so you will have two extra nodes. So in total 1, 2, 3, 4, 4 nodes, right? And the mod psi square will look like this. Go higher, so it's going to become even, the nodes are going to become even larger. Okay. So that's how your wave function is going to look like for a particle in an infinite potential well. Now let's do some exercise. So I have an infinite potential well, and the width of the potential well is 5 angstrom. Angstrom means it is 5 into 10 power minus 10 meter. Can you calculate the first 3 energy eigenvalues? So please do this. Calculate the first 3 energy eigenvalues and tell me what is the range of that. So I just want to give you an impression of what is the order of these energies I'm talking about. And you calculate it for an electron. So for an electron, what is the mass? What is the mass of an electron? 9.1 10 to the power minus 31 kilograms. Please do it. N square pi square h square by 2ma square. So that's what your energy is. Okay, so if you do that, so the solution is going to be, it's a very simple calculation, but I just want to give you some idea about what will be the order of the energies you're calculating. So if you put it right, so A is 5 angstrom, right? M is this, and other quantities. So H bar is 1.054, right? It is H by 2 pi. So the Planck's constant divided by 2 pi will give you this. And if you plug in all of these quantity, so you get n square times this. And this is in terms of joules. So in terms of joules, you get an order of 10 to the power minus 19. But usually we don't talk about joule because it's a very big unit. For the quantum systems, the joule is a very, very big unit of energy. So what we do, we convert this into electron volt. Electron volt, how do you convert an energy into electron volt? You divide it by E. What is E? The charge on the electron, right? So you divide it by 1.6 10 to the power minus 19, the charge on the electron, and what you get is n square into 1.51 electron volt. So the order of energies is going to be in the electron volt. So if for n equal to 1, you have 1.51 electron volt. For n equal to 2 becomes 6.04, n equal to 3 becomes 13.5. So order is the electron volt. Okay. Okay, let's talk about, so we have covered the step number 1. Yes. So step number 1 was in the Schrödinger equation, we calculate the energy eigenfunctions. What's the step number 2? Step number 2, we multiply each of these energy eigenfunctions with their corresponding uh, corresponding e to the power minus iota e t over h bar, and that's how we can calculate. Then if we sum those up and multiply with some constant coefficients, then we get the general solution. So the particular solution of the time dependent Schrödinger equation It can be obtained by multiplying with exponential of minus iota e becomes en, right? So for corresponding to psi 1, you multiply with exponential of minus iota e1 t over h bar. For psi 2, you know, this e becomes e2. So in general, it is en, right? Corresponding to each of the eigenfunctions. You get all of these new particular solutions of the time dependent Schrödinger equation. So it has the position part as well as the time dependent part. Okay, so what do we get? So we get some kind of a psi, capital psi n, it depends on n of course, as a function of x and t as under root of 2 by a sine n pi x by a, right? This is the psi x, and then you have this exponential part, and en is n square pi square h square by 2m. H will cancel, so you just have one h. Okay, how do you get the general solution now? So the general solution of the time dependent Schrödinger equation, you will sum it, you will sum all of these eigenfunctions over n. You will take a linear combination of all of that. If this is a solution, the linear combination of all of these psi n's will also be a solution, and that's the most general solution of the Schrödinger equation. So but in this case, because this is discrete, so we are going to use a summation, not an integration. Okay, so energy eigenvalues are discrete here. Okay, so n is going to run from 1 to infinity. Remember, we discarded n equal to 0 and negative values. So it runs from 1 to infinity, and you have these wave functions psi n multiplied by some constant. So these are the weight factors or the coefficients. Yeah, so that's how you do it. Now, how do we calculate the Cn? Oh, it also arose in the free particle case, right? But in that case, we had an integration and we had to calculate phi k. Okay, so what did I tell you? I told you that you can do that by taking inverse Fourier transform of psi x comma 0. So first of all, let's try to do this something similar. Let's first try to take the wave function value at t equal to 0. So what will that do? That will eliminate this part. Yeah, so if you put t equal to 0 here, this is eliminated. So what do you get now? You get this psi x comma 0. It simplifies things a lot. So this thing is psi n x, right? Okay, how do you calculate this Cn? So I told you earlier that because so remember, in the free particle case, we had some e to the power iota kx in the psi n, and then there was phi k, and I told you that that represents, because there is an integration, that represents the Fourier transform of the psi x comma 0, and phi k we can calculate by taking the inverse Fourier transform. But I did not tell you how I reached that inverse Fourier transform equation. Yeah, so if we go back, yeah, here, right, we took the inverse Fourier transform. But how I obtained this, I did not tell you. I mean, if you have done the mathematics, right, any mathematics course which involves the Fourier series, and also you already know this. But yeah, we did not look into phi, and I just told you that this is just a formula. Okay, for inverse Fourier transform formula, and you can calculate the phi k from here if you know this. Yeah, integrate over dx. So I'm now going to give you an intuitive picture of how we obtained this, but I'm just going to do it for the Fourier series, not for the integration one. Integration one will be similar. Okay, but you will get the idea. Okay, so we have this. Now what we do to calculate these Cn's, what we do, let's multiply both sides. Let's multiply both sides with an energy eigenfunction. Okay, but a complex number of, I mean the complex version of that. I mean you take the conjugate. So I'm going to multiply both sides with conjugate of an eigenfunction, and that eigenfunction can be any eigenfunction, right? So say that eigenfunction is psi of m, and I multiply both sides by psi m star. Yeah, we can do that, right? So as your psi n is an eigenfunction, there will be some psi m where m or n may not be equal, right? So n runs from 1 to infinity, right? So this is 1 2 3 4 5 6 7 8. Say I multiplied with psi of 8, right? Or in general you can assume any m, right? M also varies from 1 to infinity, but this can be any m, any one m among these all the available eigenfunctions. I pick any one eigenfunction, I call that psi m, and I take its star and I multiply it both sides with this and integrate with respect to x. So what do we get? You get this. You multiply it with psi m star and integrate over minus infinity to infinity. Similarly, you multiply it with psi m star and integrate over minus infinity to infinity. That integration will go inside the summation, right? Because it's simply a constant, and these are just, assume these, see, look at these as the summation of the terms. If you integrate every term, right? So and then again you want to use the summation symbol, so you can write it like that, right? So that integration is directly going to go over this, okay, because this is simply a constant. So minus infinity to infinity psi m star psi n dx. Okay, now what do we do? So we want to calculate the Cn, right? But before that we need to evaluate this quantity minus infinity to infinity. Let's evaluate it separately. Okay, so evaluate this integration, so we get this. So minus infinity to infinity psi m star psi n dx. By the way, in the bracket notation, this is going to be the dot product of psi m and psi n. We talked about that yesterday, right? It's exactly that. So it's a dot product of psi m and psi n. Yeah. So that bracket notation I used, right? And this is going to be equal to minus infinity to infinity. You can put the value of psi m. So what will be the psi m? Root 2 by a. It's a real wave function, right? Root 2 by a into sine of n pi x over a. That's your psi n. So that's here. If you put n equal to m here and took it and take its conjugate, so it will still be like this. Yeah. Now you have to calculate this quantity, and integration is from minus infinity to infinity. It's not a very difficult thing to do, right? So from some simple mathematics you can do that. So first of all, that root 2 by a and root 2 by a, if you multiply, you get 2 by a, and in this part I'm going to assume that m is not equal to n. Okay, m is not equal to n, I'm assuming it. So okay, so if I assume that, so this is a different function, this is a different function. Now sine of, say, some quantity into sine of some quantity, so it's like sine of a, capital A, into sine of capital B, and there is a 2 also, so you can put 2 here as well. So 2 sine of a sine of b. Do you remember a trigonometric identity that from which you can obtain this thing? 2 sine a sine b. What's the formula? The formula is cos of a minus b minus cos of a plus b. That gives you 2 sine a sine b. Okay, so this quantity 2 sine a and sine b, so that will give you this cos of a minus b and this minus of cos of a plus b. No big deal. And the integration is from 0 to a now. So because we know that outside 0 to a the wave function is 0, so no point of talking about that. Okay, so this 2 is gone in this, right? So you have 1 by a now. Okay, now you can simplify these further. So you can convert these cos into some sine, right? So so sorry, this by integrating this cos, you will convert this into sine, right? So if you do the integration of cos, you get the sine, right? Similarly, integration of cos, you get the sine, right? And of course these are the multiplications, so you will divide it, the in the integration you will divide it by this, right? So if you have sine of some ax, the cos of some ax, the integration is going to be what? Sine of that ax divided by a. So that's what it is. Integration of this is going to give you this. Integration of this is going to give you this. Okay. And then you can simplify it further, right? Take this pi out. So this is this quantity, right? And what you have to do, so you will get that you will see that if you simplify it and open these further, you'll get equal to 0, right? You can further open these formulas of sine and cosine, this sine of m minus n, sine of m. So how you do that? You know that m and n are integers. Yes. So m and n are integers. If m and n are integer and I take the subtraction of those two, and I know m is not equal to n, right? So this is going to give you a multiplication of pi with an integer. Sine of anything, you multiply the pi with an integer in its argument, so that gives you 0. Similarly, m plus n, because m and n are integers, so m plus n will also be an integer, right? So integer times pi. So sine of anything integer times pi is going to be 0. Okay, so 0 minus 0 will give you 0. Yeah. So this integration minus infinity to infinity psi m star psi n, if you simplify that, we get a 0 when m is not equal to n. What happens when m is equals to n? So we can't use this formula, because if we use m equal to n here, so it is going to blow up. So we don't use this formula. Let's calculate it directly. What if I use m equal to n? It means I am talking about psi n star and psi n. So psi m star becomes psi n star. What is psi n star into psi n? Mod psi n square dx, and we know that that quantity is equals to 1. So now you get two things. So if m is not equal to n, you get 0. If m is equal to n, you get 1. Okay. So what do we do with this information? What is our purpose? Our purpose is to calculate Cn, right? The coefficient in the general solution of the Schrödinger equation. Okay. So in general, combinedly we can write these two conditions as this: minus infinity to infinity psi m star psi n dx is equals to some delta mn. Okay, combinedly. When m is not equal to n, so this delta is called Kronecker delta function. This is not Dirac delta. When you put a delta and you write some integer there, m n, so that's called Kronecker delta function. So Kronecker delta function means that when m is not equal to n, so this quantity becomes equal to 0. When m is equals to n, this quantity becomes equal to 1. Okay, so that's your Kronecker delta function, and combinedly you can write these two conditions by this. Okay. By the way, if you have two functions which satisfy this identity, they are said to be orthonormal functions. In mathematics, if you have two functions and you take the conjugate of one function and multiply with the second function, you take the integration from minus infinity to infinity, and that gives you delta mn. When m is equals to n, you get 1. M is not equal to n, you get 0. They are called orthonormal function. Okay, so these are orthonormal functions. Psi m star, psi n, they are psi m and psi n, they are orthonormal functions, right? And you can also write it in the form of a dot product. Yeah. So how do I write it in the form of a dot product? So I know that psi 1, psi 2 in the bracket notation. So it gives me psi 1 star, psi 2 dx. So that's called the dot product. So what about the psi m? If I write psi m psi n minus infinity to infinity, it gives me psi m star psi n dx. So orthonormal functions are those functions whose dot product is delta mn. If psi m psi n gives you delta mn, the dot product of them, then psi m and psi n are orthogonal to each other, orthonormal to each other. Okay, orthonormal means they are orthogonal plus they can be normalized. Okay, orthonormal means orthogonal and normalized. Okay, what is the meaning of orthogonality? You remember in the vectors, when the two functions are said to be orthogonal, what is the meaning of orthogonal? They are perpendicular to each other, kind of. Yes. What if two vectors are perpendicular to each other, vector A and vector B? What happens to their dot product? Becomes equal to 0. Okay, so two functions which are orthogonal to each other will have their dot product equal to 0. So this thing is basically the generalization of that. So we are talking in terms of vectors here. Here we are talking in terms of functions. So two functions are orthogonal if their dot product is equals to 0 when they are not equal. What if A and B are equal? So in the vector A, if vector A and vector B, if they are equal, what will happen? Vector A dot vector A, that will not give you 0, that will give you some number, right? A square, magnitude of A square. By normalization we mean that A square is equals to 1. Okay, so if magnitude of one vector is 1, magnitude of the other vector is 1, right? So the dot product will give you equal to 1. So these functions psi m and psi n, they are normalized as well as they are orthogonal. So when both of conditions are fulfilled, so you will get the dot product equal to delta mn. When they are not equal, you will get 0. When they are equal, you will get 1. Okay. Okay, so they are orthonormal. Now how do I calculate Cn with this information? Say they are orthonormal. If they are orthonormal, what I can do, I can plug this thing back into my equation, right? Equation number 14. So what do I get? I get this. I had minus infinity to infinity psi m star psi x comma 0 dx, right? On the left hand side. On the right hand side, I had summation n equal to 1 to infinity Cn, and I had this integration term. But that integration term is equals to delta mn. Okay. Now, if I sum up n from n equal to 1 to infinity Cn delta mn, what will I get? What will I get? This term is only non-zero. See, n is running from 1 to infinity. So it's going to be C1, C2, C3, C4, C5, C6, something like that, right? At one point, it will also match my m. Say m is equals to say 7, right? So what will I have? I have in this summation C1 into delta of, so what is n? 1, and this is 7. So what is delta 7 1? That will be 0 because they are not matching. Then I have n equal to 2, right? So this is 2, this is 7. 7 2 not matching, 0. Similarly, I will have n equal to 7 at one point. In one of the term I will have n equal to 7. So this will be C7 delta of 7 7. Yes, there is a match. So that will give you what? 1. And at that point, what is the value of C? C7, right? It means it is Cm. M is 7. Okay. Okay, so say if I now do C n equal to 8. So C8 delta M, which is 7, 8, mismatch 0. So whenever there is a mismatch, it's going to be 0. It's only going to be non-zero when n is equals to M. And at that point, this Cn is Cm. So what do you get? The result of this summation, Cm. So the mth coefficient you can calculate by this formula, right? Cm becomes equal to this. Okay, so this is precisely what we did earlier in the case of inverse Fourier transform. Something like similar, something like this. So in that case, instead of psi m star, right, because we were dealing with the plane waves, right, so I put e to the power iota. Yes, do you remember? So we put e to the power iota there. Okay, e to the power minus iota kx. So that's my psi n, the eigenfunction. Okay, now what was the eigenfunction in this problem? E to the power iota kx plus iota kx, right? So if I take the eigenfunctions here, right, so what were the eigenfunctions of the time independent Schrödinger equation? Summate e to the power iota kx, b e to the power minus iota kx, and combinedly we told you that so it's going to be some a e to the power iota kx minus omega t. If I say I am only interested in the time independent part, so it will be e to the power iota kx. Forget about this constant, so we don't need to worry about it. So the eigenfunctions were e to the power iota kx, and I took a star of that, conjugate of that. So what do I get? E to the power minus iota kx, and that's what it is. And you multiply it with psi x comma 0, integrate over minus infinity to infinity, right? So this is a constant, so don't worry about it. So that gives you the coefficient, right? So the thing I'm showing you, it's like a generalized it's a generalized way of calculating these coefficients, whether you have a summation or an integration, right? So we call this in inverse Fourier transform. Okay, now in our case, in this particular problem, what do we have? Psi m. What is psi m? So you have psi m as sine of m pi x by a. Okay, multiply it with this, right? So there is a root 2 a root 2 by a as well, so that comes outside. So you can calculate your cm by this. Okay, in general, now I can tell you this formula is actually in general valid, provided these psi m you are talking about, this psi m, it has to be an eigenfunction of the energy. Okay, if you have an eigenfunction of the energy, you can do this. Okay, any confusion? Because after this we are going to move to the next topic. Any confusion until now? No? Okay, so we already talked about the particle in an infinite potential well. Now let's talk about a particle in a finite potential well. What if those walls I showed you, the potential walls, they are not at infinity, they are at some finite value? Why this is important? Because approximately we can represent the potential of an atom by a finite potential well. Okay, So we'll see that, but uh, so we have already seen the infinite potential well, but that's not realistic. So more realistic is finite potential well. Okay, and we will approximate your atoms by this. Although that's not a very good approximation, but that will help us to understand the energy bands. So why I'm doing all of this is because this background is going to be very useful in understanding the energy band formation in the semiconductors. Okay, so let's talk about a particle in a finite potential well. Okay, what happens? So what I mean by a finite potential well is a well something like this. So say I have a potential energy U. I mean we were calling that as V. Uh, so let's call that as U, right? It doesn't matter. It's just a variable. The picture I took it from, no, I mean denoted it as U. So I've done this derivation in the form of this. Okay, so I have a potential energy U, and I have a potential well from 0 to A, and these things are finite. These levels are finite. So this is some U naught, capital U naught. Okay. So now what do I do? Again, we follow our steps. So what will we do? We will calculate the energy eigenfunctions, right? Time independent Schrödinger equation will solve that. Okay, now from this onward I won't go into the general solution, right? We know that what, see, we'll limit ourselves to calculations of the energy eigenfunctions, and we know that the general solution is some kind of a linear combination of that. So that part I will skip, right? Because that's kind of becoming redundant, right? So we'll only do eigenfunctions, right? And the rest of the part, you know what to do. So it's an exercise, right? You can do it yourself, but the most important thing is the calculation of energy eigenfunctions for the time independent part. Okay, so which regions we have? So we have a region from 0 to A, we have a region x greater than A, we have a region x less than 0. We have three regions, and in three regions I have three values of the potential. So in x less than 0 and greater than A, the potential is same, it's u naught, and from 0 to A it is 0. Okay, and I won't go into the deep into the mathematics of it, right? I will just show you how to apply the Schrödinger equations, and I won't be solving it thoroughly. Okay, so if you want, you can, I mean, pick any quantum mechanics book and look at the mathematics of it, but that's not our purpose. I mean, you that's just the mathematics. We want to understand the concept more, right? So by showing you all of this, you will be able to understand how to draw the wave functions in different regions, and you will also get an idea what happens to the energy. We already have some idea that when the particle is free, the energy is continuous, and when the particle is confined, the energy becomes discrete. So what about this? If I put a particle in this, is it confined or is it free? Is it confined or it is free? It is confined, but it is not totally confined. Okay, if the energy of the particle is very large, it can escape this well. If the energy of the particle is very small, then it will be almost confined. But even if the energy of the particle is, say, less than this u naught, it's somewhere here, you will see that, you will find that it can still escape the well. Okay, by escaping the well, I mean that there will be some non-zero probability density in these regions as well. Earlier we said that because these walls are at infinity, so the particle cannot exist in these regions. But in this problem, you will see the particle can exist in these regions, even if the energy of the particle is smaller than the level u naught. Okay, so that's a very quantum mechanical result, you can say. So classically, particle is forbidden actually. If the energy of the particle is less than this, so it will be forbidden in these regions. But here you will see it can still exist even if the energy is smaller than the u naught. Okay, So let's begin. Okay, so let's talk about the region 0 to a. So what do we have for region 0 to a? We have the Schrödinger equation as minus h square by 2m d2 psi naught by dx square plus potential energy times psi naught equal to E psi naught. Let me call the wave function within this 0 to a region as psi naught. Okay, the part of the wave function that exists between 0 to a, let me call that as psi naught. And what is the v here? V is equals to 0. Yes. So what do we get? We get this d2 psi naught by dx square minus k square psi naught. So this is our old story. We have seen this many times now, right? So you get this number 2me over h bar square. This is 0, and you assume that it is some k square, right? Where k is equals to under root of 2me over h bar. Okay. Now, what will be the general solution of this? We have seen that multiple times, right? So general solution will be psi naught x a into e to the power iota kx b dash into e to the power minus iota kx, right? So a dash and b dash are some constants. Okay, for this particular problem it will be easier if we convert this into another form, which is sin kx and cos kx. Actually you can write this thing equal to this, where a and b, capital A and capital B, are some other constants. So you can actually prove that this identity is true. Now let me show you that. So what do we have? We have this. So you have a dash into e to the power iota kx plus b dash into e to the power minus iota k dash kx. What is e to the power iota kx? Cos kx plus iota sin kx, right? E to the power minus iota kx will be cos kx minus iota sin kx, right? You multiply this with a dash, a dash, a dash, you multiply this with b dash, b dash here, b dash here. Now sum these up. So what will be the summation? A dash plus b dash cos kx plus a dash minus b dash sin kx. I'm writing this as some other constant a. So this is cos kx and this thing is some other constant, say b, sin kx. Okay, so this form is equivalent to this form. In fact, in a particle in an infinite box, many books will use this form directly. Okay, so these are equivalent forms. You can use either of them, provided when do you get this solution? When do you get a e to the power iota kx plus b e to the power minus iota kx type of a solution? When you have d2 psi over dx square equal to some minus k square into psi. There should be a minus here and it should be a positive number. Only then you get a solution like this. If you have a plus here, then that will not be a complex number. Okay. Okay. So in the next part we'll see that. So sin of x you get as some a sin kx plus b cos kx. Now let's go to the region this and this. Okay, so let's go to the region x less than 0. So I'm talking about this. So what is the value of the potential here? U naught. U naught. And what will be my Schrödinger equation? Time independent Schrödinger equation. So you have minus h square by 2m. Let me call the wave function here as psi minus. Plus, what is the potential energy? U naught psi minus equal to E psi minus. Okay, now rearrange this. So when you rearrange, you get this. So d2 psi minus by dx square. Take this. So take this quantity here. So that will be E psi minus minus U naught psi minus. and there is a minus also, so if you multiply, so you will get u naught psi minus minus E psi minus, right? And then you multiply with 2m by h bar square, so you get this. Yes. Now, important thing to note here is that now I'm going to call this constant as some alpha square, right? So alpha is under root of 2m into u naught minus E by h bar square. If you take the square here, so you get this number. Let me call this as some alpha square. Okay. And I'm assuming that my energy is less than the u naught. So my energy lies somewhere here, right? You can also assume E is greater than u naught, but we are not interested in those solutions. So the E can be inside the well or outside the well. So but I'm assuming that it is inside. So E is less than u naught, I'm assuming. So this is going to be a positive number. You can express that positive number as some alpha square. Okay. Now the important thing to note here is that what do you have here? So there was a minus here, right? And if there is a minus here, the solution is this. But you have a plus here, so the solution is going to be a little different. So solution will be psi minus x is equals to, let's call some constant a minus into e to the power alpha x plus b minus e to the power minus alpha x. So there is no iota here, it's not a complex. Okay, so we have seen that. How did we get this? So we actually expanded this exponential into two first order, expanded this second order differential into two first order differential, right? D by dx plus iota k into d by dx minus iota k, right, into psi equal to 0, right? That's what we did. We take this here on the left hand side and we expand it. Something similar we can do it here, right? So let me do that. We have this d2 psi minus dx square is equals to some alpha square e alpha square psi. Yeah, we have alpha square psi, yes, psi minus. Okay, let me now divide this operator like this. So this is d by dx. Okay, first let me take this here, d2 psi dx square minus alpha square psi minus equal to 0. Okay, let me take this outside, so this will become d2 by dx square minus alpha square psi minus equal to 0. I can write it like this. Yes, I just took this alpha this psi minus out. So what is this? What will be the solution of, so I can write it like this, d by dx plus alpha d by dx minus alpha psi minus equal to 0. Okay, what will be the solution of this? So what is the possible value of d by dx alpha and all of that? So there are two cases we can make. So first case is three cases. Psi minus equal to 0 will give you 0, but we are not interested in that, right? So that's a trivial solution, so we'll discard it. What about the other things, other conditions? So this left hand side can become 0 if this is equal to 0, or if we would have put it like this, right? We can put it like this as well. I mean, you take the plus first and minus minus first and plus later, so you can also write it like this. So if this becomes equal to 0, then also the left hand side will be 0. So we have two cases. So in the first case we have d by dx minus alpha, right, psi minus equal to 0, and the second case is d by dx plus alpha psi minus equal to 0. What is the solution of this? Can you tell me? What is the solution of this first order differential equation? So what is this? D psi by dx equal to alpha psi minus. Yeah. So what do you get? D psi by psi minus equal to alpha dx. Integrate both sides, right? What do you get? ln of psi minus equal to alpha times some x, right, plus some constant, say some c naught. And if you take the exponentials both side, right, so what do you get? So you get psi minus here and e to the power alpha x plus c naught. You can write it like e to the power c naught into e to the power alpha x. This, let me call this as some a minus e to the power alpha x. Similarly, you can also get the other solution from this, and you will get psi minus equal to some b minus e to the power minus alpha x, because when you, there is a plus when you take it on the right hand side, so this will become minus. Okay, in general, right, if this is a solution, this is a solution, the combination of those will also be a solution of this differential equation, this differential equation. If psi minus equal to a minus into e to the power alpha x and b minus e to the power minus alpha x are solutions of this, you can actually check the combination of those two, the summation of those two will also be a solution. So in general, the most general solution of that equation is this. That's what I have written here. But the thing to notice is that this is not a complex quantity, it's a real number. Okay, it's a real number. So why it's a real number? Look at this, right? So alpha is equals to root of 2m into u naught minus e by h bar, and u naught is greater than e, right? So that will be positive. So under root of a positive quantity will give you a real number. Okay, so this is what you have in this region, x less than 0. What about x greater than 0? Oh, before that we also need to do one more step. Okay, so we got this. Okay, now I have two unknown coefficients. By the way, we have several unknown coefficients. So we have two here, right, a, b, and I have two more. Now can I simplify it further? So I have a minus e to the power alpha x and b minus e to the power minus alpha x as the general solution in this region. But now think think in terms of some physical thing also. So if my x is tending to say minus infinity, what will happen here? This term will become equal to 0, right? So alpha is positive, e to the power alpha minus infinity, e to the power negative of very large number will give you 0. What about this? If x is minus infinity, so this will become e to the power alpha into infinity plus infinity. So that will blow up this exponential. It means when you go to x minus infinity, this wave function is going to blow up. It's going to be very, very large. Is that possible? It basically it's going to become infinite. Now what did we say? The wave function has to be finite everywhere. In fact, it can be proved that if you have a wave function, right, and if you have a finite potential at x equal to infinity or minus infinity, the wave function should actually go to 0. From the Schrödinger equation, you can prove it. I'm not going to go into the detail of it, but you can prove that whenever you have a finite potential, may not be a constant, right? It could have been any finite potential as a function of x. At x equal to infinity and minus infinity, the wave function has to go to 0. Okay, provided potential is finite and not a function of time. Okay, so but in this case, forget about the finite, we are getting infinite at x equal to minus infinity. So how do I save my wave function from becoming infinity? I know that it cannot happen, right? If it cannot happen, this b minus will have to be 0. That's the only possibility which can save this psi minus from becoming infinity at minus infinity. Okay, so this b minus is going to be equal to 0. Okay, b minus has to be 0, otherwise this is going to blow up. So you are only left with the plus term, e to the power alpha x. Okay, Now let's talk about the region which is x greater than greater than a. So what do you get? You again get an equation like this, right? It's exactly the same situation. You have the same potential. You have the same potential u naught, right? So this alpha remains the same. So what is the alpha? Under root of 2m into u naught minus e divided by h bar. So alpha will still be the same, right? Because when you solve the Schrödinger equation, you will still get the same alpha. But these constants may change. So let me call these constants as a plus and b plus. Now again, in this particular wave function, I cannot have a plus as non-zero, because if a plus is non-zero, then e to the power alpha plus x. So if x tends to plus infinity, see, x is greater than a I am talking about. So it means I am talking about a region where x is positive, and what can happen to it? X can go to plus infinity. So this is going to blow up. The only way to save it is to make a plus equal to 0. So what are we left with? Psi plus is equals to b plus into e to the power alpha x. Okay. So now you have seen all the three regions, right? All the three regions. Yeah. So in this region, I have some kind of a sine and cosine. So some kind of an oscillation. Yes. So this is some kind of a sine and cosine, a combination of that. So I will have some oscillations of the wave function here. What about this region? I have a wave function which is exponentially. What will happen to this? This is an exponential function with some positive alpha, and if I am going to x negative, what will happen to this? This is going to decay, right? If you make x more and more negative, this is going to decay. So I have an oscillatory function here, but I have a wave function which decays. Similarly, for x greater than a, I have a plus e to the power alpha x, but x is positive. Sorry, a plus into e to the power minus alpha x, right? So sorry, b plus. So b plus into e to the power plus alpha x. Okay, alpha is positive. There should be a minus here. It's a typo. Let me correct it. Should be minus, right? Because this is the term e to the power minus alpha x. Yeah. So what happens to if x tends to say plus infinity? So this is going to decay, right? If as you increase the x, this is going to decay. So you will have a decaying wave function in this region. So you have decaying like this, then you have oscillations, then you have a decaying wave function. Okay, I'll show you the exact plot, but before that, let's talk about the boundary conditions. Okay, so we have to apply the boundary conditions, and we have seen in case of an infinite potential well what kind of boundary conditions we applied. So at x equal to 0 and a, the wave functions were 0, but the same boundary conditions we can't apply here because it's not 0, right? So the wave function may not be 0 at x equal to a and 0. So what kind of boundary conditions we can apply then? So these are the boundary conditions that we apply. So what you have, we know that the wave function has to be continuous everywhere, right? It cannot be a discontinuous, because discontinuity means at the same point you have the two values of the probability, which is not possible. Okay, so the continuity of psi will lead to, at x equal to 0 you must have psi minus and psi naught. So psi minus is a wave function x for x less than 0, and for x greater than 0 you have psi naught, right? So these two must be equal, okay, at this boundary. Wave function on the left side and wave function on the right side, they must be equal. Similarly, at x equal to a, psi naught and the wave function on the right hand side, psi plus, they must be equal. Okay, so that's the continuity of the wave functions. In fact, you can go a step further. You can also say not only the wave function must be continuous, it has to be differentiable also. Okay, it means their derivative, the derivative of the wave function, the derivative of the wave function, it has to be continuous. Why is that? Why is that the case? You know that in the Schrödinger equation, you have to calculate the derivative of psi, right? The double derivative. If d psi by dx, it is not a continuous function, right? If psi is not differentiable, then what will happen to this term, right? So for this term to behave properly, you have to have psi which is continuous as well as differentiable. Okay, so the first boundary condition is at this boundary, the second boundary condition is at this boundary, and that leads to the continuity of the wave functions. But their derivatives must also be continuous. So at x equal to 0, the derivative on the left hand side must be equal to the derivative on the right hand side. It means uh, this. Okay, at x equal to 0, d psi minus over dx equal to d psi naught by dx. Similarly, at x equal to a, d psi naught by dx must be equal to d psi plus by dx. So this is the continuity of the derivative of psi. Just means that the function is differentiable. If you do that and plug in all of these conditions, so what you get is this. So these relations. Okay, so what you will do, you will put this, for example, psi minus 0, right? You put that into, so what was that, a minus into e to the power alpha x. You put 0, so that will give you a minus. It must be equal to psi naught 0. What is psi naught 0? Psi naught 0 was a sine kx plus b cos kx, something like that, right? If you put 0 here, so you will get b cos kx, and x equal to 0, so cos kx will become equal to 1. So what you have, left hand side you got from the psi minus, right hand side you got from the psi naught, and that will make a minus equal to b. Similarly, if you put psi naught a equal to psi plus a, so what do you get? So psi naught is what, a sine kx plus b cos kx. So instead of x you have a, so you have a sine ka plus b cos ka, right? And what is psi plus? So psi plus is this, so put e equal to e to the power minus alpha x equal to a, so it should be minus again, there's some mistake, minus a. Okay, so you put x equal to a here, that will give you minus alpha a. Similarly, what do you have? So you have equation this, so you take the derivative of d psi minus dx, d psi naught by dx, right? And you put x equal to 0 0 here, you get this equation. And if you take these derivative, you get this equation. You can calculate it yourself, I'm not just calculating this. Okay, so you can do it yourself. So these are the equations that you get. Now this is some kind of a relationship between the coefficients and the k, right? The coefficients, how many coefficients we have? A, b, a minus b minus, a plus b plus, 6 coefficients. So this is a set of equations that relate those coefficients, plus it also relates your k. K is also appearing here. So what you can do from these, so a minus is equals to b. So where does a minus appear apart from this? So hey, so this has to be a, okay, b plus, yeah, somewhere here, right? So a minus equal to b. Okay, so b you can calculate. So a minus equal to b, if you put here, right? So you will get Ka over alpha, right? Ka over alpha. A minus and B are both equal to Ka over alpha. Okay, so you can reduce these equations like this, and then uh, what else do you need? So you have A sine Ka, B cos Ka, and you have B plus into e to the power minus alpha A. Then you have this equation. Okay, so K from this equation you can take in the denominator. You get the everything in terms of B plus. This should be A minus equal to, I think this should be, okay, let me see, sine not 0. No, so this is correct. You can put A minus here. Yeah, so what you can do, so in this equation, so I got A minus equal to from this equation in terms of A, because A minus is equals to B, so B can also be calculated in terms of A, right? So everything A minus and B both can be calculated in terms of A. Now you have this equation, right, which has A and B. Now if I put B in terms of A, right, which is Ka by alpha here, so everything will be on the left side will be equal to on the left side will be in terms of capital A. Okay, and then you have this equation. From these two equations, then you can obtain another equation, which is this. So you can eliminate all of those constants. You can do that, right? It's just some elimination technique, and after some mathematics you get this. Okay, and if you further want to write it in terms of, say, if I divide so if I divide it by the cos, so this sign is going to become 10. It should be equal. Okay, so this sign will become 10 Ka, and this will go in the denominator, right? So 2 alpha K, and cos, sine by cos will become 10. So what I want to tell you from this, see, mathematics is one thing, yeah, you can do that mathematics, all of that, right? So after applying the boundary conditions, what you get is a relationship of K and this alpha. Now K is what? K is related to energy. Alpha is what? Alpha is also related to energy. It means this is an equation fully in terms of energy. Yes, because K is a function of energy using this. Alpha is also a function of energy using this. If you plug both of them here, so it will mean that your energy has to follow this constraint. Energy has to follow this constraint, right? It means energy is not now anything. It cannot be any real number. It has to be a number. It has to be a value which follows this. Okay, it has to be a number which follows this constraint. Yeah, so it turns out that only a few of these solutions will be possible. Only a few energy values will satisfy this, right? So this is an equation, and the solutions of this are the values of energy, and only a few of them will exist depending upon what is the value of this small a and u naught. Okay, what is u naught? U naught is that the depth of the well. Okay, depending upon what is the depth of the well and what is the extent of the well, the dimensions of the well, you will get some solutions of this equation. Finite number of solutions. So in the case of a infinite potential well, how many energies values we had? We had discrete energy values, but they were still, if you count them, uh, they were infinite, right? E1, E2, E3, E4, E5, E6, and so on up to n equal to 1 to infinity. So you had the discrete values, but the number of eigenvalues were infinite. Here you will see that this is some kind of a equation, and this is going to give you only a finite values of energy depending upon the value of the dimension A and this u naught. Okay, so what you get is something like this. So for example, if your u naught is very small and you have some A, only one solution is possible, only one energy is fitting into this well. If you have a u naught which is deep enough, so there can be some finite number of energy eigenvalues which fit into the well, right? There can be solutions which are outside the well, but we are not talking about those. We are talking about the solutions for which E is less than this u naught. Outside the well there can also be some solutions, but inside the solutions only 4 will fit for this particular case. Similarly, if you keep say increasing the depth of the well, more solutions will fit inside the well. Okay, so an example is given here. So this is your well from 0 to A, and only 3 energies are fitting inside the well, and corresponding to 3 energies we also have wave functions. So first wave function, which is the ground state energy, looks like this. Remember, inside 0 to A we have some kind of a sine and cosine. Outside we have some kind of a decaying exponential. Always remember, whenever the energy is larger than the potential in a region, if the energy of the electron is larger than the potential of potential energy of electron in a region, then you will get some kind of a sine, cosine, or some e to the power iota kx, some kind of oscillation, some kind of a wave. If energy in a region is less than the potential energy, for example this region, the potential energy is here and the energy is here, so then you will get some kind of a decaying wave function. Similarly here, decaying wave functions. Okay, if you go to higher energy eigenvalues, so what do you get? You get different wave functions. So first you get an even wave function, then you get an odd wave function, but the behavior remains the same. So there are some kind of an oscillations here, some kind of a sine or cosine, but here you get a decay. Similarly, again you get, so even, odd, then again even, some kind of oscillation, but then decay. Okay, and you can see that when the energy of electron is small, it's not penetrating into this region much, right? So what does this mean? The finite value of wave function means the electron can exist here, because mod psi square will give you a finite probability here, right? It means electron can spend most of the time here, but it can also spend some time here, it can also spend some time here. Okay, because there is zero probability, there is a non-zero probability here and here. Now classically this is not possible. Classically, so what is the energy? Energy is your total mechanical energy, and if your total mechanical energy is less than the potential energy, is it possible classically? It's not classically possible, because the total energy has to be equal to the sum of kinetic energy plus potential energy. If your total energy is less than the potential energy, it means your kinetic energy is negative. So classically that is not possible. Kinetic energy has to be positive, right? It's half mv square, it's a positive number. Classically it's a forbidden region, but quantum mechanically it is possible. Quantum mechanically the particle can leak into these regions which are classically forbidden. Okay, even if the potential energy is higher than the total energy, the particle can still exist in this region. And as you can see, as you increase the energy of the particle, the leaking becomes more. You see, it decays very quickly, but it decays a little at a little larger x, right? It decays later. Similarly here, right? If you increase the energy more, it leaks into these regions even more. Okay, so depending upon the energy of the electron, it may leak into this. So if E1 becomes much smaller than compared to U0, so then it will not leak. For example, if you have these finite if you had this U0 tends to infinity, right? So then U0 becomes much larger than any of E1, E2 and E3. So then you will see that the particle will not even enter here, right? As U0 increases, this decay becomes quick. So it's going to decay more and more quickly, right? And for an infinite potential case, the particle will not decay at all. I mean, it will be zero here. It will not decay at all means, I mean, it has already decayed, so that the wave function is zero here. Okay, so so these are the solutions of the finite potential well. Okay, now we know that qualitatively we know that whenever the energy is greater than the potential, so we get some oscillation. Whenever the energy is less than the potential energy, we get some kind of a decay, right? Now using this concept, we can also qualitatively see another uh, problem, which is the potential barrier and tunneling. Okay, what is the meaning of a potential barrier? So potential barrier means this. So we till now talked about a well, right? A well means you have some level of potential energy, and then the potential energy is smaller. Uh, this means a potential barrier means you have a potential energy zero here, but then you have a barrier of potential energy, some finite potential energy. So say I have an electron which I incident from left side to the right hand side. Okay, so when the electron reaches here, so see, up to here the electron energy, say electron energy lies somewhere here. Okay, at this level, up to this level, up to this region, this electron energy is larger than V equal to 0. Okay, but as soon as electron enters this region, the energy becomes smaller than the potential energy. Now classically this region is forbidden. Particle should only exist here and here. Okay, either the particle will exist here. If I incident the particle from this side, so it will exist here. If I incident the particle from this side, it will only exist here. And if I incident the particle classically from here to here, right, it can't cross this region and reach the region number 3. It will just bounce back. So if you incident the particle from left to right, it's just going to bounce back from this potential. It will return back. Okay, classically not possible. Similarly, if I incident the particle from this side to this side, it's just going to return back. It's not going to cross it. Unless the energy of the particle is greater than that, it cannot cross. But quantum mechanically, again, this is possible. Okay, we saw that the wave function may still be some finite value if even if the energy is smaller than the V naught. Okay, so now let's try to draw the wave functions in region 1, 2 and 3 and see what is happening. Yeah, so from our previous experience we can say that the energy, whenever the energy is greater than V naught, right, a flat V naught, oh, sorry, flat 0, so this is 0, right? If energy is greater than 0, so there will be some kind of an oscillation. Yes, so something like this. So psi 1 in the region 1 will be some a1 e to the power iota kx plus b1 into e to the power minus iota kx. Yes, without solving the Schrödinger equation, now we can say this. Okay, some kind of oscillations. In the region number 2, what will happen? What will happen in the region number 2? I know that the particle has to decay. The wave function is going to decay. It has to be some kind of exponential of x. It will not be e to the power iota kx, but it will be some e to the power alpha kx or something like that, right? So in general, I can write in the region number 2, I have a2 e to the power alpha kx plus b2 into e to the power minus alpha kx. So it has to decay, exponentially decay. Okay, what about the region number 3? Again, the energy of the particle is larger than the potential energy. So then I again will have a wave function similar to psi1, a3 e to the power iota kx plus b3 into e to the power minus iota kx. Okay, what are the k and alpha? So we know that k is going to be equal to root 2 me over h bar, right? You can write the Schrödinger equation and you will get exactly these values. Okay, so alpha is a positive quantity and energy is less than v naught, so it's a positive number, positive real number. Now, can we draw the wave functions here? Yes, we can. So how will the wave functions look like? Look like something like this. So for x less than 0, you have some kind of oscillations, then you have a decay, then again oscillations. Okay. Classically, it is not possible for the particle which has the energy less than v naught to cross this barrier. Not possible, it will bounce back. But quantum mechanically, the particle can leak from region 1 to region 2, region 3. This phenomena is called tunneling. So particle has tunneled to region 3, which is classically impossible. Okay, it has tunneled because the wave function is non-zero here. So there is a probability of particle being here. Now what about the amplitude? See, the amplitude here is larger, so it means if you take the mod psi square, the particle has a larger probability of being found here. Yeah, and then there is a barrier and it tunnels into the region number 3, but the probability density is smaller. Now depending upon the height of the barrier, this amplitude may decrease or increase. For example, if this barrier would have been very small, right? If this barrier would have been small, but still V naught is larger than E, then this amplitude will be comparable to this amplitude. Okay. If this barrier becomes very large, then this amplitude will become much smaller. The particle will not tunnel. So amplitude means the probability density. How much the particle has leaked into this region will depend upon what is the height of this barrier plus what is the width of this barrier. If the barrier height remains same and if I increase the barrier width, again it will become difficult for the particle to leak here or to tunnel here. If the width increases, say x becomes x equal to a becomes large, so then this amplitude will decrease because then the particle will have to spend more time here, right? And it will decay more, and by the time it reaches here, say if I increase this, right? So it will decay, keep decaying, and the amplitude will become even smaller. Okay, so depending upon the height of the barrier and the width of the barrier, if you make a very small, so then the particle can easily leak, it can easily tunnel. So both the barrier height as well as the width of the barrier, they decide the tunneling. Okay, classically not possible, but quantum mechanically, yes, it is possible, and this is called tunneling. Any doubt in this? So this slide marks the end of the quantum mechanics part. Now we will move to the theory of the solids, the quantum theory of the solids, and the energy bands and all of that. So, but before I move there, just let me know if you have any confusion in this whole thing.